All right, if you are on this page, that means you are ready to start Module 4 Bronze, and we're going to be talking about physical and chemical properties and changes of matter. If you're on this page, you're either ahead of the pacer or we're absent on our whole class lecture day. So let's review from Module 3 really quickly. Matter. We know that every element and compound is unique from all of the others. And if you know enough about something, you can figure out what it is. So we did that in Module 1 with the murder mystery. If we figure out enough information, you can figure out who did what or what something is. If you know what a substance is, you can know all types of things about it, but that's because they're all the same. So water is always water, Its properties are the same. Gold is always shiny. It always has the same gold color. It always has the same density. All of these are properties, things that describe it, things that identify it. So you, right now, your height, every single day that you wake up, unless you are still growing, you're the same height, you're the same weight, you have the same hair, you're the same identity, your DNA is the same. The same can be said for matter. So all matter has two types of properties, things that describe it, characteristics. Physical properties and chemical properties, and that's what this module is about. A physical property is a characteristic of a substance that can be observed without changing the substance into another. So I can see it without looking into something else. So for instance, I can tell the color of an orange without changing it into a lemon. And you should be writing this down. So if you are at home, please pause this video and write down this definition. Physical properties can be one of two things, extensive or intensive. Extensive properties depend on the amount of a substance that you have. And intensive properties don't depend on how much you have. So let's see an example. And again, these definitions should be written down. So, extensive physical properties, volume, mass, weight, and size. So the mass of my stack of pennies is going to depend on how many pennies I have. Same with how much space it takes up. Intensive properties, though, are things that never ever change. Density, melting point, boiling point. Physical properties in general, though, are properties that you can see and observe with your five senses. So you don't have to do any kind of experimenting in order to see them. So that's color, hardness, odor, how something smells, the taste, the state of matter that it is in, texture, the luster. Luster is going to be a huge word in quarter 2. Its flexibility, whether or not you can bend it. That's also called malleability. Whether it conducts heat and electricity, so its conductivity, can it spread those two things? Is it soluble in water? Does it have high or low solubility? Shape, viscosity, how sticky is that material? Does it stick to the sides? Does it flow? So water is far less viscous than maple syrup. Ductility, can you flatten it out into sheets or wires? And then malleability, again, is like flexibility. So I want you guys to take a minute and pause this video and list as many physical properties as you can for this item. So for me, I know I'm looking at sugar cubes. So it's square shaped, it's light, it's crystally, it's got luster. I would talk about how it smells, what it feels like. It has a rough texture, things of that nature. Those are all physical properties. Chemical properties, on the other hand, are what you observe when you change it into a different substance. So it's how it behaves. So some examples here. Whether it's flammable, can it burn? Does it tarnish? Does it rust? How does it decompose? Is it reactive with other chemicals? Is it stable or unstable? And can it do acid-base reactions? So things that you would say, gasoline is flammable. That means it is easy for it to light on fire. Baking soda has a high reactivity with vinegar, and that's also an acid-base reaction. If it's corrosive, so for the decompose, that would be called corrosive, things like that. So if I'm looking here at a piece of wood, what are some chemical properties that I could say? So here I know that wood is flammable, so I would say that. It doesn't decompose in a really harmful way, so I would not say that it is corrosive. It is reactive to things, but it's also stable. These are some of the things that I would say. So you may be wondering, what's the point of all of these things? Why do we need to know chemical and physical properties? What does that teach us? But it teaches us how we can make all these huge advances in science and daily life. So for instance, titanium doesn't rust, so we use it in jet engines. It's also non-allergenic, which means that we can put it when you get your ears pierced or any piercing that you have, and then artificial joints. So a lot of people need to get their joints replaced, a hip replacement or a knee replacement, and we can use titanium to do that because we know that it won't hurt your body. And then knowing these chemical and physical properties, knowing how something behaves in a certain scenario, means that we can make huge advancements. Tungsten is a filament, so tungsten is W on the periodic table. It's a filament in light bulbs because it has the highest melting point. That means that that light bulb can get super hot and the metal will not melt. So it glows red when electricity runs through it. It's conductive and it gives off both heat and light. Vanadium is heavier and harder than titanium. So if you mix vanadium with steel, you can get tools that are really strong but not super expensive. So that means it's more cost effective. So it just lets us figure out the best way to do things. Helium, what we put in the balloons and makes your voice sound funny, is completely non-reactive. It is a noble gas. And it's lighter than air, so that's why we make the floating balloons. And then it glows a pale peach color when you run electricity through it. So you could make helium lamps that have that specific color. The next is pennies. So we used zinc-plated steel because copper was being used in the war. And the pennies had to be coated with zinc because steel rusts, but the zinc won't, and then we wouldn't have a whole bunch of rusted pennies, those green pennies. The last couple real world uses. Sulfur smells terrible. If you've ever been to Sulfur Springs, it smells like rotten eggs. And stink bombs use sulfur to create a bad smell, but it's flammable, so we also use it in gunpowder. So again, knowing what it smells like gave it a market for tools, and then also knowing how it behaves gave us a market for tools. Both of these things helped us make and invent something. And then the last is chromium. I'm sure you have seen chrome wheels or chrome-plated things. Chromium has a huge shine, so we use it in jewelry, and silverware, and car parts, because it has extreme luster. Then lead. Lead is used in pencils, that's graphite, and it's also used in bullets because it's extremely dense. But then you have to coat them. You have to coat lead bullets in something else because they melt at such a low point and you can bend lead so easily. So if you just go through the rest of these, it lets you know why we're studying these particular elements, why we want to know about them. So density here is a physical property, and iridium has the highest density with 22.6 grams per centimeter cubed. And it also lets us know how much we have. So the most common element in the universe is hydrogen and helium. It makes up the sun. The most common element on Earth is oxygen and also silicon, but not as much. The most common element in your body are oxygen and carbon. So knowing these, it lets us figure out what we can use, what we need to react with. So if I know my body's mostly oxygen, then I don't want to be putting anything in it that has a negative reaction with oxygen. So I need to know the chemical properties of oxygen, and I need to know the chemical properties of that element so that some reaction does not occur. The next thing we're going to talk about is chemical and physical changes. So you talked about the properties, the descriptions, the characteristics. Now what happens when we actually alter those? So a physical change is a change in a substance that does not change what the substance is. So that means that if it changes in shape, in size, or in phase, if I melt an ice cube and now it's water, both of those are still made of H2O. If I boil water, then I have steam, which is still H2O. So changing the state of matter is actually a physical change. And you can cause physical changes by physical means. So grinding something, cutting something, crushing it, bending it, breaking it, heating it, and cooling it, or squishing it. Any of those things will change the size or the shape. So how you know a physical change has occurred includes a change in shape, a change in form, a change in size, a change in phase, and they're normally reversible. You can normally get them back. I can put water back in the freezer and it will be ice again. So just something to think about. What are some things you could do to these items to cause a physical change to occur? So I could cut the orange, I could melt that ice, I could cut the cookie in half, I could eat the cookie, and it would just be in crumbs, but it would still be a cookie. A chemical change, on the other hand, is when you change something from form A to B. So it is a different thing. You've made something new. So burning is a chemical change. Rusting, tarnishing, decomposing, polymerization, all of these things are chemical changes. You cannot get these back. They are non-reversible because the chemical reaction breaks the bonds between your first item and turns it into the next. So if I burn something, I've created something. That ash that I created is a new substance. It's switched out. So it is a chemical change. There are 5 types of chemical reactions that cause changes to occur. You will learn about those in quarter 3. But there's also a lot of evidence for chemical changes occurring. 1 is a color change. 2 is a change in smell. 3 is a formation of a precipitate. So here in this picture, you will see 2 liquids being mixed together, and a yellow solid is forming in the middle. That is not a color change in this picture. That's a picture of a precipitate. Gas is formed if you see bubbles. So if we mix vinegar and baking soda, you'll get bubbles. That is a chemical change, or it changes its physical properties. During a chemical change, you can release energy in the form of heat or the form of light. And when a chemical change occurs, energy is either released or it is absorbed. So something gets colder or it gets warmer, darker, or lighter. A chemical reaction that releases energy in the form of heat is called exothermic. Heat comes out, it will feel hot. So if you mix hydrochloric acid and aluminum, you will get an extremely exothermic reaction. If heat is absorbed, then it's called endothermic. Heat goes in, it will feel cold. So making ice cream from milk and rock salt, then it will feel really cold. That is an endothermic reaction. So let's go through some quizzes here. Which life cycle here is most similar to a chemical change? Is it the grasshopper or the butterfly? Which one would be making something new? Everyone should have answered the butterfly. You went from a caterpillar and then you went to a completely different adult. Versus here, it was just growth. That's a physical change. All right, fireworks. Is this chemical or physical? Fireworks is a chemical reaction, chemical change. All right, cooking an egg, is this chemical or physical? This is a chemical change. You cannot uncook this egg. And the last one, melting ice. Phase changes are always physical changes. If you have any questions, please let me know.